Hi, hello. Hope everybody is well. So, we're working our way through Chapter 6. This is going to be Chapter 6, Section 3, Difference in Proportions. So, the basic idea here is that we have different areas, but we're applying the same ideas over and over again. So, in Section 6.1, we were looking at a single proportion. In the second section, 6.2, we were looking at a single mean. Now here we find ourselves looking at a difference of two proportions. Later on we'll find ourselves looking at a difference of two means. But at the moment this section 6.3 is a difference of two proportions. So the easiest way to think of section 6.3 is that you're going to test two different groups. Let's say the treatment and the control group, or let's say men and women. So you're going to ask, men and women to perform some task. What percentage of men agree? What percentage of women agree? This kind of thing. So you have two different populations. You end up with two different proportions, and the question is, are they really different? Again, another example. Suppose we took first-year students and asked them are you satisfied with the food in Alio? And then we took fourth-year students, seniors, and asked them, are you satisfied with the food in Alio? And we look at the two proportions. Of course, the question is, when we do that, we get a difference. I don't know, maybe first year students are 45% satisfied, and maybe seniors are 52% satisfied. And the question then is these are sample numbers. The question is there really a difference, or did we just happen to get a sample? When you pick two numbers, one of them comes out higher. Is this just one of those things? Okay, so that's always the case. We deal with that in two different ways. We have confidence intervals, we have hypothesis tests. Confidence interval tells us where the true number lies, where we think the true number lies. If we did a census of every first year student at St. Michael's and every senior at St. Michael's, we'd know the true difference. We're not going to do a census of every first year student and every senior. It's just a waste. So instead, we're going to take a sample of the two, and we have a sample difference. The question is the sample difference tell us, yes, there is a genuine, real difference, or is the sample difference just simply a sample thing? Suppose the sample difference came out to be 1% different. I think you'd say, it's probably just a sample thing. There probably is no real difference. Suppose the difference between the proportion of first-year students and the proportion of seniors came out to be 80%. You'd say, wow, there's a tremendous difference. I'm confident. Well, of course, then we want to know, for the intermediate numbers, what conclusions can you draw? Okay, so we have two populations. In the example I was just listing, it was first year students and seniors, might be men and women, might be treatment and control, might be lots of other things. Okay. We want to know, we come up with some difference of proportions. We want to know is that, how much evidence is there that there's a real difference if we did a census instead of a sample? Okay, and as always in section 6.3, what happens is that we're coming up with some formulas that will tell us what we need for confidence interval and what we need for hypothesis test, and we worked through in chapter 3 and 4. We did the hard work of working through, of understanding what a confidence interval is and understanding what a hypothesis test is. And so now when we're applying the formulas, that's all easy. Nobody ever says to me these formulas are blowing my mind and nonsense. Of course, you never hear any such thing. People always say, okay, you just drop it in. Sometimes people say, I flubbed it up, I forgot to divide by, but that's just a flub. That's not really a serious matter. Okay, so we have two proportions and we're interested in the difference. For example, suppose we found that 48% of first-year students thought Alio was good, and 56% of seniors thought Alio was good. So there's a difference between those two numbers. We want to know, is that a difference between is that just a sample thing, or is that a genuine difference between the two populations? Okay, and here are the formulas. You see the word normal there in the shape. So I've warned you that each one of these formula sets has some small twist to it. That's fine. And the last twist, the twist in the single mean, was that we had to use this T curve instead of a regular normal Z curve. Well, we're back to a normal Z curve. This is going to be a normal Z curve, and there's always a center and there's always a spreadedness. Of course, I'm going to do an example in just a second. So the shape is of interest because we have to know which place in Stat Key to look the answer up. The center is it's just a formula, and the spreadedness is again just a formula. It's not the world's nicest formula, but come on, we have calculators. It's not it's not awful stuff. Okay, so I want to do an example of this here. I want to do an example from section 6.3. It's called section 6.3-D, and of course each of the sections in the each of the 6.1, 6.2, 6.3, etc. are broken down into 3 separate parts. So I'm doing the first of the 3 separate parts. Let's see if I can manipulate the windows correctly. Ah, there we go. Oh, what do you know? Okay, so there we are, 6.3D, distribution of a difference in proportions, and a person sees the formulas that I just had up on the slide. In particular, that standard error formula is easy to recognize, and it's easier to read on the slide, so I've been going with the slide. Now, I'm reminding you, though, don't forget that there is a single place in the book, I have a marker here, page 478, that has all these formulas, and of course you can write in whatever you like there, whatever other formulas, and in particular you'll recognize there's the formula with that oddball formula for with the square root that we're going to be working on today. And so it says z. It says, see how the previous one says t and that says z. And so we're working here with this particular formula all in one place, and it says difference in proportion. So I think bookmark that somehow. I mean, like I use an index card or use whatever you like, a paper clip to find that page. So when you're taking the quiz or whatever, you're not saying to yourself, oh, where the heck was that thing? Okay, so back we go, and I'm going to do one for homework. What is it? 132 it says. So I know it's hard to read on this camera. Can't get the camera to focus quite right, but it's not awful either. So 132 says, samples of size 300 from a population A with proportion 0.15, and samples of size 300 from a population B with proportion 0.20, and they want me to find the standard error and determine whether the sample sizes are large enough. And, of all the things that we do, I've been playing down the whole normal curve stuff, so I'm simply going to do part A. It isn't that this is foolish. It's just that in the present circumstances, I'm talking down some things that I think are kind of less central, and so we're doing A. Okay, so I'm going to take the numbers from 132, and you should of course look at the book. You can have it online, and or the paper book, whichever you have, and sort of play along. Play along with me, see if you can follow what's happening, and I want you to then, I'm going to ask you to do some homeworks. 132 is actually one of the homeworks I'm going to ask you to do, so if I was you, I would kind of close my eyes and try to forget that you had seen it before. Okay, so this is number 132. 132. Okay. And it says population A has a p hat of 0.15. Oh, I'm sorry, population A has a p of 0.15. So population A has a p equals 0.15. Remember, you always convert the percentages to a decimal. That way, when you plug them into these formulas, you won't get confused and put 15 instead of 0.15. And sample of size 300. And population B, and again, you can imagine it's men and women, for example. So population B is going to be sample of size 300. That's right, 300 with a p equals 0.20. Okay, and they want me to calculate this formula, this somewhat awkward formula, but it's just a formula. I got a calculator there, and I'll take it out and use it in just a minute. I've got a calculator, and I'm not afraid to use it. So it's going to go P1 times 1 minus P1 over N1, P2 times 1 minus P2 over N2. It's big enough that it gives a person trouble with a calculator if you try to get it all in one go, so I usually do it in a couple steps. But again, it's just a calculator job. It's not the worst thing in the world. So how do I go? Square root of P1 times 1 minus P1. We've seen that pattern before. What's happening there is you get 0.15. And then what's the opposite of 15%? Why, it's 85%, 0.85. and I think the number was 300, right there, 300. Okay, and then likewise with the P2. So 0.20, 0.20, 0.80 over 300. Add them up together, take the square root, see what it comes out to be, and that's the answer. Now anybody can flub up the calculator part, that's for sure. But again, it isn't actually the hard part. Okay, so let's see how I do. 0.15 times 0.85 equals, divided by 300 equals, and I got to tell you, personally, I write down these intermediate numbers. So it's 4.25 times 10 to the minus 4. That means 3 zeros and then a 4. So square root of 0.3 zeros and then a 4. Do you remember scientific notation? Because the decimal point is after the 4. So 1, 2, 3, 4. That's what the 4 means there. Okay, and there's a 2.5 that I didn't write down yet. All right, let's try it. And then 0.2 times 0.8 equals, divided by 300 equals, and I get same thing with the 04 there, so I'm going to write down 3 zeros and a 5. So 0.123 and a 5, and I think that's good enough for this. I'm not all that interested in the fifth decimal place kind of stuff. This is a practical class. All right, I'll add those two numbers together as best I can. So 0.000425 plus 0.000533 equals, and it says 9.58 times 10 to the minus 4, and I could write that down. That's nothing wrong with that, but I can also just take the square root at this point, and the whole scientific notation stuff disappears, and I got 0.03. So this is approximately 0.03. And in the context of 15%, 20%, a standard error, a spreadedness of the curve of 3% doesn't seem crazy. So the standard error, the spreadedness measure of the curve, in a context of 15%, 20%, a spreadedness of 3%, it seems perfectly sensible. So anybody can punch a wrong button. Maybe I punched the wrong button and just committed it to video. But I don't think that it doesn't seem wildly crazy. Okay, so that was 132. They just wanted me to work away through the formula and calculate the answer, just because it's not the world's easiest formula, that's all. Okay, next we come up to confidence intervals, and in a second we're going to go to hypothesis. Whoops, I clicked on the wrong one. There we go. And there we go. So next we're going to come to confidence intervals and hypothesis tests. So, oops, having a lot of trouble with my mouse today. Been a long day. There's confidence intervals. There's hypothesis tests. Same kind of stuff. There's always these little twists, and I'll show you the little twist in the bottom. That's fine. We've dealt with little twists before, but confidence intervals never gives anybody any trouble. Obviously, a person can flub up the calculation, but never gives anybody any trouble for the formula. The trouble is always, what does a confidence interval mean? And we paid an awful lot of attention to that. I hope that a person is starting to feel like I've seen it again and again and again, and I'm starting to get it. Okay, so for confidence intervals, I want to do problem number 148. Let's see if I can bring that over here. 148. And the hard part is clicking on all these windows. There we go. 148, there it is. Metal tags on penguins and survival. And you probably can't read it here, but you have it available to you in paper or online. Okay, so data on page 10 discusses a study designed to test whether applying metal tags is detrimental to penguins. One variable examined is the survival rate 10 years after tagging. Scientists observed 10 of the 50 tag penguins survived compared to 18 of the 50 metal tag penguins survived compared to 18 of the 50 electronic tag penguins. So it says conduct a 90% confidence interval, the difference in proportion surviving to metal and electronic, PM minus PE, and interpret the results. Okay, so they give me a bunch of numbers to calculate the percentages, and then I'm going to drop them into the formula. They want metal to come before electronic, just so I don't know that, so that the answer in the back of the book is the same for everybody, I guess. Okay, let's see how I do with that. Turn this upside down so there's no confusion about where I'm writing. Okay, so let's see. I think metal is 10 out of 50. So, what number? 148. Okay, so this is metal. So PM is 10 out of 50, and that's 0.20. And of course, NM is 50. It says right there, 50. I'm going to need N in the formula, so I wrote it out as separate. Okay, and then there's electronic. I forgot already. Is it 18 out of 50? It is 18 out of 50. So PE is 18 out of 50. I don't know what 18 out of 50 is. Oh, I probably do. 36.36. 0.36. And NE is 50 again. Okay, and the confidence interval formula, I had it up on the previous slide, but I'll write it up there now. So we're looking at P M minus PE plus and minus Z star by the square root of, and then this ugly square root formula. It's going to go PM 1 minus PM over NM, PE 1 minus PE over NE. And again, I can't overemphasize that a person can flub up the calculation, but we understand what we're doing at this point. We are trying to find not where are the sample numbers, but instead where are the, excuse me, I forgot to put the hats, Ooh, forgot to put the hats, too many hats, I'm tired of all these hats. Okay? So we're not interested in the sample numbers. We're interested in the population numbers. Where is the if we didn't do 50 penguins, if we did 50,000 penguins, and we didn't do 50 penguins, we did 50,000 penguins, and we know the true numbers. That's close enough to a census for our purposes. But we didn't do 50,000. We did 50. So we're working with the sample numbers to try to gain information about the census numbers. We want to find an interval in which we think the census number lies. PM minus PE without the hats. Okay, let me take out a calculator and see how I do with this, see if I can manage to flub this up. So 0.20 minus 0.36, 0.20 minus 0.36, plus and minus, I forgot what level of confidence I'm supposed to have, 90% confidence, so 1.645. That'd be a good number to write on that page where all the formulas are. You know, the Z stars for 90, 95, and 99. Write them all on that page. Square root of. So it's 0.20, 0.80 over 50, 0.36, 0.64 over 50. And again, anybody can hit a wrong button, but I think we're done. You know, of course I'm going to punch out the answer, but I think that this is not the hard part. Okay, the hard part is understanding what a confidence interval is. This is the easy part. Okay, so let's see how I do on the easy part. I'll probably get it wrong. So 0.2 times 0.8 equals divided by 50 equals, and you got to deal with this scientific notation. So that's 2 zeros and a 3. So square root of 0.0032. Remember how scientific notation works? It says 3.2 times 10 to the minus 3. So I got to go move the decimal 1, move the decimal 2, move the decimal 3. That puts it right there next to the 3, which is what it says on the calculator. Okay, and then the other half, 0.36 by 0.64. 0.36 times 0.64 equals divided by 50 equals, and I got a 4.608 times, so this is 0.004608. And you can round that a little bit. I'm not all that interested. What is this, the 36th decimal place? Come on. Anyway, I wrote down what I had. Okay, still the 1.645, the plus and minus, 0.20, so that's minus 0.16. All right, let's add these things together and take the square root. So 0.0032 plus 0.004608 equals, take the square root, equals, and I got 0.88. So this is minus 0.16 plus and minus 1.645, and that becomes 00, no, just 10 times 0.088. And again, for our purposes, 2, 3 decimal places is good enough. We're not worried about the 8th decimal place. I just keep it in here just because I had it on the calculator. Okay, off we go here. So this is 1.645. So 1 point, oh, you can't read it. 645 times 0.088 equals 0.14. So this is minus 0.16 plus and minus 0.14. So minus 0.16 plus 0.16. No, darn it, I don't know how to work the calculator. So let's see. I always forget this part. You know, I never paid for calculators. I always find them hanging around after people leave on final exams. And in this particular one, I'm not perfectly sure how to work the calculator. So 0.14, take away 0.16. Gives me minus 0.02, so minus 0.02, that's the high spot. And the low spot is going to be if you take 0.16 minus 0.14, so what am I looking at there, 0.30? 0.30 with a negative sign. Okay, so anywhere from 2% to 30% below. So the question then is, what's in there? What does the interval mean? And as always with confidence intervals, we did a sample. We don't know where the sense is. We think the sample is not perfectly right. We think it's close to right, but not perfectly right. How far off? This far off. So we think that the true number, that PM minus PE, no hats, lies in there. So this is not the sample number, this is the census number. We're not going to do a census of all penguins in the world. But if we did a census of all penguins in the world, we think it would lie between these two values. Okay, so as always, confidence interval, and hypothesis test for that matter, is we have a sample, we'd like to know a census. We can't take a census, talked about that for the first 2 weeks of class, tried to make a really big impression that census is not really possible. So we have to engineer our way around the fact that we're working with samples. Okay, so the engineering here is the engineering. This is what I meant by engineering our way around, is that we come up with an interval in which we think the census number would lie. How sure are we? 90% sure. The census number, PM minus PE, metal minus electronic tagging, lies in there. Okay, so that was confidence intervals, and then the next one must be hypothesis tests, and for sure, let's see how I do. Oops, I brought up stack key by accident. There we go. Okay, so that's the confidence interval, and it just proved to be a matter of punching out the numbers, not the world's hardest thing. And the other part is hypothesis test, and same sort of idea. There's a formula there. You take P1 hat minus P2 hat, take away 0. Pardon me. And then divide by, and it says, it doesn't say P1 hat, does not say P1 hat, it says P hat. And P hat, well, what's that about? What happened to the P1 and the P2? Remember with the hypothesis test that the null hypothesis people think these two are the same number. So they think that you did not actually take 2 samples. They think you took 1 sample twice. So they think that the true number you should be using is the same number for both, because they think this. And what is that number? It's the number of successes in the first case, the penguins with metal, for example. The number of successes in the second case, the penguins with electronic, for example, over the total number tried for penguins with electronics, for example, the total number tried with penguins with electronics. So in other words, they aggregate the two, what you think are two different, but they think are the same. They aggregate into one number. And of course, we're gonna do an example of that. Of course, we are. Get rid of this paper here and bring over the example. The example is, my calculator's hiding the number, 6.162. So let me find 162. And let me bring it up. There we go. Okay, so 162. If I can get all this stuff here off my desk. 162. Babies learn early who they can trust. A new study indicates that babies may choose not to learn from somebody that they don't trust. A group of 60 babies were randomly divided into two groups. Each baby watched an adult express great excitement while looking into a box. The babies were then shown the box and either had a toy in it so that they thought the adult could be trusted, or else it was empty so that the baby learned the adult couldn't be trusted. The same adult then turned a push-on light with their forehead, and the number of babies who imitated the adult's behavior by doing the same thing was counted. The results in table 6.10 test at a 5% level to see if there's evidence that babies are more likely to imitate those they consider reliable. So there's a table there, and of course we're going to take the numbers from the table. Okay, so let's see how we do. Excuse me. Okay, so I'm thinking here that the babies, 162. So P1 is going to be the reliable. Adult. So P1 was 18 out of, let's see, what's 18 plus 12? 18 out of 30. 18 out of 30. Where did I get the 30 from? It's 18 plus 12 because they had a total of 30 babies. Okay, what is P2? That's of course the unreliable, the liars. Unreliable adults. And that was 10 out of 30. And again, where did I get the 30 from? Well, on the unreliable row, there's a total of 10 plus 20, so I got 30. Okay? And I got to make up a hypothesis test here, and the hypothesis H0 and HA. So sometimes you have to read the question a couple times to figure out what they want you to say, but I'll read the last line here. Test at a 5% level to see if there's evidence that babies are more likely to imitate those they consider reliable. So again, more likely to imitate those would mean a higher percentage. More likely to imitate those, and we're seeing that it looks like, just on the face of it, it looks like a higher percentage. I'll punch the calculator in just a second. So I'm thinking that they want me to know, I didn't put sample number, and I didn't put sample number. Where is my head today? So I'm thinking that they want me to think about, if you didn't take a sample of 30 and 30, if you instead took thousands of babies and did this foolish experiment on them, if you took 30,000 babies and 30,000 babies, you'd know the census numbers. We could take the hat off and we could take the hat off. But we only have a sample. It's only size 30 and only size 30, so we have these hats. And we're arguing about whether this apparent difference is a real difference. Okay, so what's 18 over 30? 18 divided by, no. 18 divided by 30. 60, so that's 0.6060, and 10 out of 30 is of course 0.33. 0.33. Okay, so I think the argument is about whether the sample difference is big enough to persuade us that there's a genuine difference. What is genuine difference? Genuine difference is you're not arguing about the samples, you're arguing about the true numbers. You're arguing about not the sample number P1 hat, but instead the census number P1. And not the sample number P2 hat, but instead the census number P2. And H0 always has an equal sign. H0 is, we are thinking about whether, H0 is the people who think that there's nothing interesting happening here. The whole box thing sounds like a bunch of baloney, and I think that it's the same. I personally like to write it as P1 minus P2 equals 0, because it makes it look like the previous problems in this chapter, but you can do whatever you like. Okay, so we've gone through before how you make a hypothesis test. And so the hypothesis test is always going to have equal sign, in the top line. And you're always going to have the census numbers, not the sample numbers. Not P1 hat, but P1. Not P2 hat, but P2. Always the census numbers. All right, so going across the way we do it, the question says babies are more likely to imitate those they consider reliable. So we would expect this number to be bigger than this number. P1 bigger than P2. or said algebraically the same. P1 minus P2 bigger than 0. And 60 minus 33 is indeed bigger than 0, so that's kind of a check that what we're saying is at least somewhat sensible. So again, the hard part with these is not the doing of the formulas. The formula's a little ugly, but the hard part is not the doing of the formulas. The hard part is always understanding what it is we're writing down. Okay. So we're arguing about the census numbers, P1 and P2, not P1 hat and P2 hat. We know those numbers. P1 and P2 are the census numbers, and those we don't know. That's what the argument is about. We're arguing about are these two census numbers the same? And this business with the box is just a bunch of hoo-ha, and you happen to get samples that were a little different, don't get excited. Or is there a genuine difference? And if you did this with thousands of babies, you'd find a genuine difference. And this 60 minus 33 is evidence of that genuine difference. Okay? Okay, so ready for the hypothesis test. Let's go. What's the first two words of hypothesis? It's always same two words. Assume the null hypothesis. Okay, so the people in the front of the Holiday Inn in Kansas City say to the people in the seats, well, the people in the seats say, I think this is just sampling stuff. I don't think it's anything interesting. The people in the front say, suppose you're right. Suppose it was just sampling stuff. I think 60 minus 33 is so different than 0. That's not going to be believable. So you assume H0, then mathematics gives you. It has nothing to do with people's opinions. It has to do with mathematics. Then the sampling distribution and it always looks the same way, whether it's a T curve or a Z curve, always looks the same way. It's going to be centered at 0, because that's what these people think. When you say assume H0, you're thinking, that, okay, well, they think it's 0. And it's going to have a spreadedness, and the spreadedness is going to involve that ugly square root formula, but it's just a calculator job. Now again, the twist in this particular formula is that you have to work not with P1 hat and not with P2 hat, but instead with what the book calls P hat. So P hat is you take the 18, you take the two samples and combine them. So what's the number of successes? 18 plus 10. And what's the total number of babies? 30 plus 30. So that's, what's that, 28 out of 60? I don't know, 28 out of 60. 28 divided by 60 equals 47. When I round it to 2 decimal places, 0.47. And you use that number in this very ugly formula. I'm going to scoot away here just for a second. Oh, scooted away in the wrong place. Scoot away just for a second here. There we go. You use that P hat in this formula here. Okay, and that's what this part down here says. It says take the two samples and combine them into one. Okay, so here we go. Back to the piece of paper. I've got to take the square root of 0.47, 0.53 over 30 plus 0.47, 0.53 over 30. Now these two are the same, but in general you don't have to have the same number in the sample as in the other sample, so they could be different. Let's see what my calculator thinks of all this stuff. 0.47 times 0.53 equals, divided by 30 equals, and I got, it says 8.30 times 10 to the minus 3, so keeping up my general pattern, I have 0.0083 plus 0.0083, and two significant digits is good enough for us. So 0.0083 plus 0.0083 equals, take the square root, equals, and if I punched out the right ones, of course, then I got 0.129. So this is all approximately 0.129. 0.129. So that's the spreadedness of this curve. That's 0.129. All right, okay. Then where is our sample? I'll try to draw the same curve there. I'm not very good with the drawing. Not very good with a lot of things. So our sample is what? 0.60 minus 0.33, so what's that, 0.27? And I want to know the p-value. So to calculate the p-value, you always work the same way. You take 0.27 minus the middle, because that's the middle, divide by the spreadedness, 0.129. 0.27 divided by 0.129. Nope, didn't right. 0.27 divided by 0.129 equals 2.09. So that's about 2.09. I got to ask that key, what's the p-value associated with a z-score? What's the p-value associated with a z-score of 2.09? How rare is this? Is it so rare that the H0 people will say, well, I guess I was mistaken? Or is it an everyday? And the H0 people will say, I still think it's just a sampling thing. Okay, so I'll pop up stat key and ask it what's the z-score associated with 2.09. Let's see how we do. Oh, there it is, stat key. Hey, on my screen there, it's a little bit. Okay, so normal curve. Make it look like the picture that I had on the piece of paper, so that means a right tail. And down here, not high enough. What's going on? Sorry about that. So 2.09. 2.09. 2.09. Okay, I think I did that right. And the p-value is 0.18. A p-value of 0.18. So that's way less than 5%. That's about 2%. Okay, let me get rid of this stuff. Okay, so the p-value is 0.018, and that's less than 5%. Wasn't I told 5%? Yes, that's less than 5%. It's about 2%. So we found that 0.27 was actually rare. So these folks are going to say, really that rare? Okay, I guess what I'm saying is really not believable in the context of your experiment. In the context of your experiment, what I'm saying is really not all that likely. Again, in the context of your experiment, what I'm saying, this is what H0 says. In the context of your experiment, what I'm saying is not very likely. It's only about a 2% chance. So I guess your experiment provides evidence that causes me to change my mind. Reject H0. Okay, so same hypothesis test, all the same ideas. The formulas, formulas are a pain in the neck. Well, we don't do the derivations or anything, but we just take a calculator and punch as best we can, and anybody can make a mistake. But the ideas, this is the hard part. This part here, that's annoying really more than anything. You're looking for a rare, and a z-score of 2.09 proves to be rare enough. Okay, very good. Of course, I'm going to ask you to do some homework, and you should look on the assignment sheet that's in the files area of Canvas. But and I'm going to do a slide of a couple of those. But again, circling around, we are in a context where there are two percentages. So if you're saying to yourself, suppose 2 years from now I'm in economics class, how do I know what formula to apply? And the answer is because you say to yourself, well, there's a percent for men and there's a percent for women, or there's a percent for Kenya and a percent for Ghana, or whatever it is. And you say, okay, so that's a 2% case. So I have to use the 2%, the two different percent formula, and here we go, we went through it and talked about it. The hypothesis test idea is exactly the same as it was in Chapter 4. The confidence interval idea is exactly the same as it was in Chapter 3. That's the hard part. The actual formulas part is not the hard part. Okay, very good. So I hope that everybody is doing well, and we'll see you when I come back to do the problems. Very good. Bye bye.